Welcome back to the third chapter of the complete CapeExt tutorial, where we build a 3D virtual prototype from the ground up and evaluate and improve touch performance along the way. In the previous chapters, we built a board and evaluated touch performance in a simple mechanical setup that consisted of one flat plastic overlay on each side of the board. We found some problems with the touch performance and used a combination of PCB layout software and CapeExt's built-in PCB editor that allows designers to make quick PCB changes without taking the detour of changing the layout and generating new Gerbers. The final modifications to the PCB were done after we had tried quick modifications within Capext and validated these. So we ended up being satisfied with the performance of the board with the flat overlays. Now it's time to let the PCB meet its intended mechanical design and see how it performs there. But first, some theory on how 3D mechanical designs work in the virtual world of Capext. Capext imports 3D structures as STL files. In most cases, the STL file is broken up into a number of submodels that make up the total model. A submodel is a 3D mesh where any point in the mesh is connected to any other point in the mesh via at least one vertex. The submodels are arranged as a simple hierarchy where there is one parent submodel, this will be the largest one, and several child submodels. The parent only differs from the children that the children can inherit the materials property of the parent submodel. And when the parent model is moved, the child submodels will move with it. Also, if the scale of the parent submodel is changed, then all the child models change accordingly. Child submodels can be moved between models. They can be assigned the role of a parent within its own model, or become the parent of a new model. Priority. If two 3D structures overlap the same volume, Capext resolves that conflict through model priority. The volume defined by the overlap is assigned the properties of the structure with the highest priority level, meaning the volume will be the lowest priority number. Note that the priority of any submodel can be changed, and this will change how Capext interprets the overlapping volumes. Layers defined in Capext always win the volume battle as they are assigned priority 0. Then the submodels from the STL files follow. When Capext imports STL files, the child submodels are assigned the highest priority levels available, and the parent is assigned one priority level lower than the lowest priority child submodel. Clicking the up and down arrows changes the submodel priority. And that completes the model theory section of this tutorial. Now let's start building our virtual prototype. First, we remove the plastic overlays we applied to test the board without the 3D structures. Then we select Use 3D Models and right-click here to import. STL files have no information on the dimensions or scaling, so expect some trial and error to get this right. For STL files exported from Blender, the scaling factor is 1000, so we'll use that. The model will never report with the correct orientation and placement, so be prepared to do some work on that. Without a model that contains a representation of the PCB, this is almost impossible, so consider making this a part of your workflow. We first get the rotation right. Then use 2D view along all three axes to move the body in place. It is sufficient to align the object along two axes, but we also check the third axis to make sure that everything is aligned properly. And it looks like we have placed the PCB and the 3D model correctly relative to one another. Then we check lock 3D objects to prevent us from accidentally moving the 3D model relative to the PCB at a later stage. Now, as we learned in the model theory section, the PCB defined by Capext always gets priority over any part of the 3D model. It is still a good idea to hide the model PCB to prevent that misalignments alter the results. The final stage of building the virtual prototype is assigning the materials properties. You may want to work with your material supplier to establish the correct permittivity figures, but using the defaults in Capext may be sufficient. Before we do that, we mouse over the submodel hierarchy and identify the submodels we want to assign names to make them easier to identify at a later stage. Now, the body is our parent model, and since most of the board is made of plastic, it makes sense to keep the default settings where all child submodels inherit the materials properties of the parent, and then override the one submodel that deviates, namely the battery. Note that when I go back and reselect that the child submodels should inherit the materials property of the parent, I only do that to collapse the list. Since the battery no longer has its materials set to custom, it will stay metallic. And as a final check, we use Capext's cross-section viewer to verify that our 3D model is accurate. And just like that, without 3D printing or PCB manufacturing, we have built an exact prototype of the final product that we are now ready to start measuring on. And that we will cover in the fourth and final video in this tutorial series.